In this section, we'll discuss about carbonyl alpha substitution, acidic hydrogen, and keto-enol tautomerism. Now, carbonyl alpha substitution, let me explain that to you. This is C double bond O is a carbonyl group, and I may have carbon on either side of this carbonyl group, and that's alpha location. Next to alpha would be beta. Next to beta is going to be gamma. So that's how you label these locations of carbon as you go away from the carbon double bond O. So this is the carbonyl group, and among all the hydrogens bonded to carbon, alpha hydrogens are more acidic than hydrogen coming from other carbon. So in other words, these hydrogens are more acidic than the hydrogen at the end. So this is the end. Okay, so let me highlight those more acidic hydrogens. This is alpha, so that's acidic. This is also acidic. And on the other side of carbonyl, these are acidic. So keep that in mind, that we recognize which ones are acidic hydrogens. Now in this particular case, you're seeing this carbonyl group, and next to carbonyl group would be called alpha location. If that carbon in alpha location has hydrogen, then it would be called alpha hydrogen. Now these alpha hydrogens are more acidic than other hydrogens attached to carbon. For example, if you have CH3CH3, let me show you that as an example. So if you're comparing with this molecule CH3 and then you have say another CH3, it looks a little messy, CH3CH3. Now in this particular case, the hydrogens are not that acidic at all in comparison with this compound. This is quite a bit more acidic than this. Why? Because of this kind of electron movement or delocalization of electron pair from, you can see it here, we call it tautomerism. Now here we're showing you mechanism how you can get enol formation in presence of an acid. So in presence of an acid, you can see here the acidic hydrogen first going to protonate this oxygen. So H plus would make it positive, and then you can write down two structures like this. This is the resonance structures, because nothing is moving at this point yet, but eventually it's going to move. But I'm saying that in base catalyzed enol formation, OH minus first contributes. You can see here OH minus has 3 pairs of electrons. It contributes its electron pair to hydrogen, in this case this hydrogen. And hydrogen, as it makes a bond with that oxygen, it has to give up electron pair from here onto carbon, because hydrogen cannot make bond with, or cannot have more than one pair of electrons. When that happens, this carbon gets negative charge. OH minus takes this hydrogen and becomes H2O, which is not shown in this slide, but that's what happens, H2O. And so this is the negative charge, and that negative charge is not localized here. You can draw a resonance structure. Here we're going to use the term resonance, because as I move this electron pair from here to here, this electron pair will move to oxygen, and in other words, you basically come up with this structure. This movement of electron pair stabilizes this intermediate, and basically once you have this structure, bottom structure, that takes up one H plus and gives you enol, because this is alkene group, this is alcohol group, and that's why it's called enol. Now here we're showing you all these different locations of carbon. So the first adjacent carbon that could be on either side is alpha. So this is alpha, and these hydrogens are more acidic than other hydrogens. The next location is called beta, next is gamma, next one is delta. Now we're showing you a reaction where you see how alpha hydrogen gets removed and you can have a substitution reaction. Like this is the compound you're looking at, which has carbonyl group. Let me use a different color. This is carbonyl group, and this is the alpha location. So you have alpha location on both sides. So let's now focus on one of these sides, and which has methyl group. Remember, carbon must have 4 bonds, so this carbon also must have 4 bonds. And this hydrogen is acidic, so obviously Br is going to replace that, because hydrogen would get out and Br would take place. And that's how you can get this reaction. We're not thinking about the other possibility which can also happen, which is on the other side of carbonyl group. Now, from this compound, in presence of a base, pyridine is a base, it can lose hydrogen. Let me show you. This carbon has 2 hydrogens. This is one hydrogen, this is the other hydrogen. In presence of a base, one of the hydrogens would be gone. So this hydrogen is gone, taken up by the base. So that base is going to grab that. And what is going to happen is, Br is a good leaving group. So this goes over there and Br gets out. So you get a double bond here in presence of a base. Let's try to name these compounds that we discussed in last slide. The first one is 2-methyl cyclohexanone. Now why 2-methyl cyclohexanone? We already know that this is cyclohexanone, and functional group has to get 1, so this has to get 2, so that's how it goes. So that's my second location of a methyl group, so that's why it's 2-methyl cyclohexanone. Now in naming the next one, again it's the same idea. The functional group has to get 1 and this gets 2, but there are 2 substitution groups now. One is methyl, the other one is bromo. Now you need to go by alphabetic ordering, so bromo comes before methyl. So 2-bromo, then dash 2-methyl. Always between number and letter there should be a dash. So this is 2-bromo, this is 2-methyl, the second location, so you have to write down that location twice for 2 substituent groups. Cyclohexanone, again you have cyclohexanone. Now let's try to name the third one, this compound. Again, functional group gets 1, then 2, then 3, then 4, that's how it goes. This time it is going to be 2-methyl cyclohex. Again, it's 2-methyl, this is the methyl group. So 2-methyl cyclohex, 2-in, because that's the location of the double bond. 1-on, that's the location of carbonyl group, or C double bond O. Now here we also wanted to remind you this, that alpha bromo ketones undergo elimination reaction because Br is a good leaving group, and we discussed that in last slide. And you get alpha beta unsaturated ketone. This is what you see here. This is alpha beta unsaturated ketone. Let me go over one homework problem, which is 11.4, page 378. the question is, what is the bromination product for following reactions? So I'm going to do first part A, 4A, and I'm going to write down the reaction CH3, then you have CH, another CH3, and then you have C double bond O, and then CH, then you'd have CH3 and another CH3. Basically, we're asking for, in presence of bromine and acetic acid. So in presence of bromine and acetic acid, what bromination product you're going to get. First, you need to find out which ones are alpha hydrogens. So look for the location of alpha first, alpha carbon. This is alpha carbon adjacent to carbonyl oxygen. This is the carbonyl group. This is the other alpha. And those hydrogens, which if there is any hydrogen bonded directly to those carbon, those are acidic. So this is one acidic hydrogen, this is the other acidic hydrogen. So either of these hydrogen could be replaced by Br, and they're going to give identical product. So that's why I'm just going to write down the final product of this reaction. There's going to be CH3, and then you'd have CH3. Here you'd have now Br. Let me show you that. I'll highlight that again. And then C double bond O, C, that's remain intact because we only removed one of the acidic hydrogen, CH3. Make sure you count number of carbon atoms so that we didn't make any mistake. 1, 2, 3, 4, 5. There should be 5 carbon atoms. There is a carbonyl group, and of course we have methyl groups too. So this is going to be the final product of this reaction, in which you'd see that alpha hydrogen is replaced by a Br group. This is the Br group. Let me now go over part B. Part B, there's cyclic compound, and it has hexagonal ring. That's hexagonal ring. Now carbonyl group, and they have 2 methyl group on one side. Let's first identify the alpha hydrogens. So adjacent, this is the one alpha hydrogen alpha location. This is the other alpha location. And any hydrogen that is bonded directly to this alpha carbon would be the acidic hydrogen. So let me draw that, because carbon must have 4 bonds. So these are the 2 hydrogens you need on that alpha location. But this carbon, I'm showing you with the red dot, cannot have any hydrogen because it already has 4 bonds. So these are the 2 hydrogen, those are acidic. Either one would be replaced by Br2. So let me show you that reaction. Br2 in presence of acetic acid, So what I'm going to get next, hexagonal ring, the double bond O, and methyl groups, and one of the hydrogen would remain intact, but the other hydrogen would be replaced by Br. So this is the bromination product. So basically in this kind of reactions, first identify location of alpha carbon and then location of the hydrogen directly bonded to that carbon. And those hydrogens are acidic and they could be replaced by a group like Br. Now here we're showing you pKa values. This is simple alkane. pKa value is quite large. And next one with alpha hydrogens. This is the alpha location because this is the carbonyl group, the alpha location. So we have 6 hydrogens in alpha location. 3 coming from right hand side and other 3 be on the left side. The pKa is substantially lower, 19.3. I discussed that in one of those chapters that smaller pKa value means stronger acid. So this is going to be a stronger acid. And why is this stronger acid? Because it has alpha hydrogens. So these are the hydrogens. That makes it a stronger acid. There is another way of knowing it. If you get rid of hydrogen, then you end up with this product. This is called carbon. This is actually a product where carbon has negative charge because the hydrogen has left, and you want to examine when hydrogen leaves as H+, how stable that carbon minus is. In other words, you'd be looking for possibility of resonance where electron could be distributed or could transfer, negative charge can transfer from one location to the other. Now we can readily draw structure. Resonance structure. I'll show you. Electron pair can go from here to here. Then carbon, this carbon would have too many bonds, so it has to break its double bond and releases this electron onto oxygen. So you end up with this. So because of these kind of structures, and we often show with double arrows, this negative charge species are quite stable, and that's why you'd expect something like this, and that's why hydrogen can leave, creating this negatively charged carbon. On the other hand, in top structure, let me show you the top structure. If hydrogen leaves, you'd end up with something like this. But can this electron go anywhere? Answer is no. Say for example, if you want to move those electron pair, say try to bring it in between 2 carbon, then this carbon would have too many bonds. But there's no way it can do anything here because you're not allowed to break any bond in resonance. So basically, this kind of resonance structure would not happen. In other words, electron pair on a carbon in this structure is not very stable. In other words, nature is not going to favor this. So on the other hand, nature is going to favor this, and you'd expect those hydrogen, you'd expect this hydrogen, acidic hydrogen, to leave because the anion that they form is stable. Now here we're showing you another example with pKa value substantially lower, 4.7. Now why this is so much lower? Because of this carboxylic acid group. Now COOH, this hydrogen can leave a lot more readily than the hydrogen from alpha location. In this case, this is the alpha location. Why this hydrogen? Let me show you with red. Why this hydrogen can leave more easily? Because the fact this oxygen is pulling electron away from hydrogen. So also there is another electronegative element on this side. So overall, there is a flow of electron, or there is a pull of electron away from the hydrogen, and hydrogen can leave quite readily. Now when hydrogen leaves, you'd expect a resonance structure, and that's what we're showing you here. See, double bond OO minus. Can that minus be distributed somewhere else? Answer is yes. Let me show you how this can happen 4, 6. This electron pair, let's move it in between carbon and oxygen. Then yes, this pair of electron can move onto oxygen. We haven't moved any atom here or didn't break any oxygen carbon bond. Only thing we broke is the pi bond, and which is quite all right. Here we're showing you a reaction of sodium hydride with cyclohexanon. Sodium hydride separates into sodium plus and H minus, and H minus has a pair of electrons. Let me show you that pair of electron. That pair of electron, it goes to this hydrogen, one of these acidic hydrogens, and since it's acidic hydrogen, it also tries to leave its cyclohexanon compound, and it would donate its electron pair onto this. So it goes in between these two carbon atoms. These are the two carbon atoms, and this carbon would have too many bonds. I've shown with asterisk. Temporarily it would have too many bonds. So in order to conserve its 4 bond, it has to break its weaker bond, weaker pi bond, and leave its electron pair onto oxygen, and you result in this compound. So this is called cyclohexanon enolate. This is enol would have H here. Since we don't have H here, it's called enolate ion. We don't call it cyclohexenon because that would be wrong, because we are calling it enolate. That itself has en and olate. En means have a double bond, so we are already naming it that way. Let me go over another homework problem, which is number 22, B, C, and D, page 396. So here you're supposed to indicate all the acidic hydrogens in different molecules. So let me go over B first, and I'll try to explain to you. This is pentagonal ring with 2 carbonyl groups. There are 2 carbonyl groups. So the question is, indicate all the acidic hydrogens. Remember alpha location. Let's first see how many alpha locations you have in this compound. It has to be adjacent to carbonyl. Let's now focus on that carbonyl. Adjacent to that would be this on one side. This would be on the other side. Now let's try the other carbonyl group. Adjacent to that would be this side. Adjacent to be same as coming from the other side. So basically these are the adjacent sides, and they're all acidic hydrogens. So let's now write down how many hydrogens we have. On this side we have 2 hydrogens, because I know that there'll be 4 bonds. So let's have 2 hydrogens, and this would also have 2 hydrogens. So in this particular case, I see there that there are 6 acidic hydrogens, and those 6 hydrogens are shown in blue. Let's go over part C now. Again, the same thing. We need to find out how many acidic hydrogens are there and which ones are acidic. So let me write down first the formula exactly that was shown in the book. CH2, then you have CH2, then C double bond O, C, then triple bond C, CH3. Let me double check. OH, CH2, CH2, C double bond O, C, triple bond C, CH3. So the question is, identify acidic hydrogen in this compound. Some of these you can find out by simple observation. They're not asking for only alpha hydrogen, it could be any acidic hydrogen. So let me put an asterisk on this oxygen, and since oxygen is highly electronegative, so it pulls electrons away from hydrogen, so this hydrogen becomes an acidic hydrogen. This is a hydrogen of an alcohol group. An alcohol, you know, that has some slight acidic property too. Now, next we can look at alpha locations. This is alpha locations. That alpha location has two hydrogens. So both those two hydrogens are acidic. So there are one hydrogen here, and there are two hydrogens here on this side. On the other side of the alpha location, this is also alpha, but there is no hydrogen, because that carbon already has 4 bonds. But you have to also think about whenever you have a double bond, triple bond in conjugated manner, like in this case, conjugated means this is a single bond followed by a triple bond. So there is a possibility of resonance. So let me show you this side of this molecule. It would examine whether these hydrogens are acidic or not. So let me show you with that second half of that molecule, showing you separately so that I can explain to you. So it'd be C double bond O. I'm just writing that part of the structure. Triple bond C, and then I'm going to write down CH3 like this, because we're examining whether these are acidic or not, these hydrogens. Now remember how we tested? Let's assume that hydrogen is gone and it will leave behind a pair of electron. So when you have pair of electron, would that be stabilized? Let's see whether there is any resonance possible. Remember resonance? You try to relocate electron pair or distribute electron pair without breaking any covalent bond, like in this case carbon-hydrogen bond or carbon-carbon bond. So if this electron pair comes here, then this carbon has to get rid of its electron pair to that adjacent carbon-carbon bond, and that carbon also would have now too many bonds, so that has to dump its electron pair onto oxygen. So basically in this half of the molecule, something like this would happen. That's minus. You have a double bond here, C. Now you have a double bond here, C. Another double bond here, C. And two hydrogens. Remember, we are checking whether resonance would be possible. And indeed, a resonance structure is possible where electron pair moves from this location, shown with blue asterisk, to this location. So that's going to stabilize this N carbon with electron pair. In other words, nature is going to favor removal of hydrogen as an acidic hydrogen. So now we get these three also acidic hydrogens. So let's write down that. So basically we have 6 acidic hydrogen in this compound. 3 of them are due to resonance, even though they're not in alpha position, but because of the resonance, negative charge is delocalized. And 2 are in alpha position on the left hand side, they're acidic, and 1 hydrogen is acidic because it's attached to OH group. In the same way, you can work on part D, but let me give you the hint to do part D so that you can do it. So let me draw part D. It's a benzene ring. You remember the benzene ring? It's a 6-membered ring structure. Double bond, single bond, double bond, single bond, double bond. So that's benzene ring. you would have C double bond O, O, CH3. And then you'd have CH2. I'm going to write down CN more explicitly so that you can see what kind of bonding you have. Now, alpha location of this carbonyl group would be on its left side, but there's no hydrogen bonded there because this carbon has 4 bonds, so there's no hydrogen there, so that's cannot be acidic. These hydrogens cannot be acidic either because they're bonded to carbon, and carbon is not a very electronegative element compared to hydrogen. The difference is not that big. So there is no such possibility from this side of the molecule. Let's look at the other side. What about this hydrogen? Now there is the possibility of resonance, because if I remove this hydrogen and electron pair is sitting here, I can expect resonance like this. So in other words, I can move this electron pair from this end to this end. And when nitrogen is electronegative, when it gets negative, that's pretty much a stable situation. And because of that, all these hydrogens attached to this carbon, so there are 2 hydrogens, are acidic hydrogens.